Okay, so intermolecular forces are weak relative to intramolecular forces. Intermolecular are weak pseudo bonds between molecules. So they're the forces that arise because of polarity. They're the forces that arise on the outsides of molecules. So if you have like molecule A and another molecule of A, then there's some type of, let's say like this end of molecule A is partially positive and this end is partially negative. Well, likewise on this molecule, that side will be positive, side will be negative, and what happens is it forms an attraction between this negative and this positive. Okay, so you'll see that, and I'll try to be consistent. I like to use these green dotted lines to show intermolecular forces. So there's several different types to look at. So there's what are called dipole-dipole bonds. This is with this what I just drew up here. Here, this I just drew a dipole to dipole. So it's a result of this molecule being partially negative on this side, and well, the same molecule has the other side of it is partially positive. So they line up like this. If you were actually able to see the molecules, they would line up like that with opposite charges forming an attractive force, an attractive bond. And this is essentially what holds molecules together when they freeze and when they condense into a liquid and then when they freeze. The force of attraction are these either dipole-dipole, um, hydrogen bonding, or dispersion forces, or sometimes these are called sometimes these are called LDFs, okay, or London dispersion forces. So that's an LDF. So back to a hydrogen bond. A hydrogen bond is essentially just a dipole-dipole bond, but it's when you have one of these involved. It's when you have if your molecule has this structure, an OH, an NH, or the molecule HF does hydrogen bonding, hydrofluoric acid. So typically you're looking for this feature or this feature, and then the molecule can do um, an especially strong dipole-dipole. So I should probably make a note of that. So hydrogen bonding is it's basically it's a dipole-dipole, but it's an especially strong one. And the reason is because of the difference between there's a big difference between En for oxygen, which is 3.5, and hydrogen is 2.1. So the difference in En there is 1.4, and that's relative to differences in Ens. That's pretty big. So it results in like a heavily partially negative on the oxygen and a heavily partially positive here. So they're big charges on hydrogen bonding. And so what it does is it makes a stronger magnitude attractive force for hydrogen bonding. Okay, these are really weak dispersion forces. However, they start to increase greatly when you get more and more electrons. So, and we'll cover these a little bit one by one on the following slides. So here's like a cartoony looking picture of a dipole-dipole interaction. So these little cartoon pictures represent a polar molecule with a positive end and a negative end. So this side's positive, this side is negative, and then they form attractive forces here. Okay. And so you don't have one or two molecules. If you have a cup of water, if you have 18 grams of water, you have a mole. And a mole would be 6.02 times 10 to the 23rd molecules of water. if you had 18 point grams, 18.02 grams of water. So what are all these molecules doing? They're doing this. Okay, so they're all lined up in a way where the negative ends face positive ends, and then you get these attractive forces here, okay, between all the water molecules. Okay, water would actually, to be more correct, water actually does hydrogen bonding. Okay, so here's hydrogen bonding, special case of dipole-dipole. And by itself, it's the strongest. If you just analyzed it like on a 1-to-1 ratio, by itself, it's the strongest intermolecular bond. You'll see that London dispersion can get really strong as you start to pick up more electrons. So it only occurs between hydrogen. So like what I showed on the previous slide, look for this feature or this feature, and it'll probably do hydrogen bonding. So here's a water molecule, here's another one, and here is a hydrogen bond. So this is our oxygen, and this is our hydrogen. And on water, the hydrogens are positive, and the oxygen is partially negative on all of them, all water molecules. This is negative. Okay, and so you get this attractive force here between the two. So if you have a whole, a cup of water, this will form like this whole network of water molecules and hydrogen bonding. Okay, and if you look at each one of these individually we have oxygen and hydrogen. Okay, oxygen and hydrogen, negative and positive. So when you so let's say this is frozen. Okay, this thing here is a giant ice cube. Okay, so what makes it turn to a liquid? So you leave the ice cube out, you drop it on the floor, makes a puddle. Couple of minutes, it'll be a puddle. What's going on? Zoom into the ice cube, and what you will see is that all these hydrogen bonds, they start loosening up when you go from a solid to a liquid. Okay, they're still there, but they start getting really, really loose. So what happens when this happens? So they get so loose that the molecules have more motion. Okay, and so there's more vibrations, and so it's not as it's not solidified, it's not crystallized as a solid. So the molecules, when these start loosening up, it starts becoming a liquid. And so what happens when you go from liquid to a gas is these more heat enters these hydrogen bonds, the intermolecular forces. So more heat starts entering there. For example, if you put water on the pot and you're going to make some soup, okay, and so or you're going to cook some pasta, you need to boil the water. And you start seeing steam. What's happening with the steam? It's going liquid to gas, but what's really happening with the steam is the heat from your stove is going into these and it's snapping them. So these hydrogen bonds are disappearing, okay, one by one, okay, and then when they start disappearing, they're not held together anymore at all, and then they start to fly away, and then you see water vapor, and then when it hits colder air, it starts condensing again, and then you start seeing steam, like little droplets of water, and so that's what steam is. So these guys are breaking these these are breaking free, and then they hit more cold air, and then you see, like steam, which is sort of like, fog, little droplets of water. So intermolecular forces, or IMFs, what are they? Well, if the molecule's polar, it's going to be either dipole-dipole or hydrogen bonding. Okay, and then the other type of IMF are London dispersion forces. And what's so great about these three things? They hold molecules together as a solid liquid, and when they fully separate, you'll get a gas. So, so dispersion forces, or LDFs, are momentary. They're the weakest of all by themselves. If you looked at it one to one. However, if you start to get around 70 electrons total on the molecule, these start to become really, really strong. So here's a picture. So let's say this is helium, because helium has two protons, and we have two electrons, one and two. Okay, and so let's say we have a sample of helium, so we have more than one, because these electrons are moving around. Okay, and so let's say we have more than one helium atom. Let's say we have another one. Again, two protons, and again, two electrons. Okay, so here's a dispersion force. Within the atom or molecule, the electrons are moving. Okay, they're whizzing around. Okay, and what happens is, uh, okay, so they're whizzing around. And what happens is sometimes, like if you were to take a picture, like a snapshot, sometimes you'll find all of these electrons arranged on, um, sometimes you'll find all these electrons arranged on, oops, okay, I couldn't get it, time it right. And there. Okay, sometimes you'll find all these electrons arranged on one side of the molecule, and what it does is it exposes these protons on the other side. So within the molecule, you get a slight negative side and a slight positive side. So what's the effect on a neighboring molecule is, these leftover protons here are on this side of the molecule, and so what it does is it pulls in the electrons on a neighboring helium. Okay, so you get a negative and then you get another positive. Okay, and this goes on throughout the whole helium sample. Okay, so it forms a momentary induced dipole just for the simple fact the electrons move. Okay, and then if we had another helium atom, it would do the same thing. So that's a London dispersion force. Okay, the attraction is just for an instant before the electrons decide to keep moving. Okay, I wanted to make a quick distinction here because I see this a lot on lots of different exams, on like the subject test, the AP exam. I probably saw it on the my credential test when I tried to become a teacher. So, um, intramolecular are covalent or ionic. So don't forget, what we learned before. So here's ionic, full-blown charge, cation, anion. Covalent is sharing of electrons. So intra is within the molecule. Intramolecular, or IMFs, is are all forces happening on the outside of the molecule. Okay, so covalent, these are really strong. So these bonds, intra, way stronger. So intra is way stronger. Intramolecular, so ionic or covalent, these are way stronger than any of the IMFs. Okay, so hydrogen bonding dipole or LDS. So I just wanted to make that distinction. Okay, so inter are the forces, remember, on the outside. Okay, so it's these red dashes here. I think a little bit ago I said I was going to make them green, but this time I made them red. Okay,